Okay, so this is work that I did last year while I was interning at Barefoot Networks. But yeah, as Ben said, I'm at Uzi. So as we're getting to the end of the programmability session today, I'm sure you all know that we used to live in the Neolithic age of fixed function ASICs. This Stone Age hardware supported some standard protocols, L2, L3 forwarding, and they were high performance, but they had fixed functionality. You couldn't really change what the underlying hardware was doing. We've come out of the Stone Age. Now we have these new switches that can be programmed without compromising the performance. People have noticed that, and they've started moving applications into the network, from key value stores to consensus protocols, from replication to ordering transactions in the network. They've seen this new hardware, and they've found an opportunity: stateful processing in the network. Given that these applications are getting orders of magnitude better performance, it's clear that they'll continue to offload to the switch. But if this trend is going to continue as it is, it may become problematic, since they're all using state in ways that was never intended. All these applications are doing stateful computation. A packet comes in, updates the state on the switch, and is spit back out. The state of the art right now is to do all this with P4. The abstractions that P4 provides are tables and packet headers. It's not inherently stateful. P4 is great for networking, but it seems that people are trying to shoehorn stateful computation into their applications. Does P4 have the right abstractions for them? What are the right abstractions for stateful processing? So this has already been answered by the stream processing community. If you think about it, stream processing is a lot like networking. They both have streams of data coming in, and they do some stateful computation. And there's a wealth of knowledge in the stream processing community, and I think it can teach us something about stateful processing in the network. But what's the best way to learn from them? The best way, we thought, was to implement an existing stream processing system and put it on a switch. This would not only show us whether it's possible, but it will also give us an idea, an insight to what's involved, how complicated it would be. And maybe we'd also see some nice performance benefits. But where should we start? What application do we pick? So stream processing isn't new. People have been building them for years. In the early 2000s, we saw some new systems. From Brandeis, Brown, MIT, we saw the Aurora and Borealis systems, which Stonebreaker later went on to make the company called Streambase. And then there's the Stream project from Stanford, which made the CQL streaming language. And they all wanted a way to test their systems, these systems that they've been building. So they got together and they created a benchmark called Linear Road. It appeared in VLDB 04, and it has since become the standard benchmark for stream processing, and it's been used by many systems. In SIGMOD 06, the IBM implemented their stream processing core and evaluated it with Linear Road. And then more recently, they also got together to implement it with Walmart. So we decided to implement Linear Road because it's a good representative application. So Linear Road is a hypothetical system that assesses tolls to vehicles on an expressway. The idea is that vehicles constantly emit their position, which a system uses to model the flow of traffic. It's a comprehensive benchmark that has queries that are representative of stream processing workloads. It has well-understood semantics, and since it's relatively small, there are only 5 queries, we thought it would be practical to implement in P4 without too much engineering effort. So what does Linear Road do? Let's take a look at the queries. The input stream can trigger any of these queries. Cars are assessed tolls when they get on the expressway, and they're also notified of accidents down the road. Cars can request the sum of tolls for the day, and they can also request historical tolls. They can even get an estimate for the time to travel between 2 exits. So we implemented all the queries here in P4 for a switch, but today I'll just show you one of the queries, the accident alert query. This query is triggered whenever 2 cars are stopped in the same lane, and all cars traveling up the road from this action should be notified of it. It's pretty straightforward to implement with some operators, some basic operators. There's some filtering, a group by, and then a projection. And let's see how this query would be implemented in P4, targeting this architecture, the RMT architecture, reconfigurable match tables. And the RMT architecture is pretty much the same thing as PISA, which you heard about earlier today. And it's not so straightforward, though, to implement that query within this architecture, because there's some fixed hardware constraints that we have to deal with. There aren't any loops in the pipeline. There's a bounded number of stages, and there's a fixed amount of memory per stage, and this memory cannot be accessed by other stages. For example, the second stage can't access memory in the first stage. And also, registers, you can only access a single entry of a register at a time. So it's not like programming your typical x86 processor. I'll show you some of the techniques that we use to implement the accident alert query. For this query, we need to update a counter that contains the number of stopped vehicles in a lane. Because the memory is local to each stage, we have to increment the counter and read the new value back in a single stateful ALU operation. And then we need to iterate through all the counters. But because there's no looping in the pipeline, we need to explicitly unroll the loop and explicitly check each of the counters for stopped cars. And because you can only access a single register entry at a time, we partition the register entries into multiple register arrays. That way we can load the entries in parallel. We can load multiple entries in a single stage. So this is just one of the queries. When we put it all together, we got this. These are all the tables in our implementation of P4, of linear road in P4. So I don't have the time to go into how all this works now, but I can give you an idea of the performance that we got out of it. So we compiled it and we deployed it on a Barefoot Tofino switch and hooked it up to an Ixia packet generator. And what we found was that we had the fastest implementation of linear road ever. 4 billion events per second. And to put that into context, one of the first implementations using the IBM streams processing language had 2 million events per second. And a more recent stream processing system, Drizzle, had 100 million events per second with the Yahoo benchmark. So this is orders of magnitude in increase in performance. But this is not an apples to apples comparison, because we didn't implement all the features that these software systems did. But that's not what we're trying to do here. We're trying to explore what the right programming interfaces are and what the limits are of what you can do with this hardware. We wanted to generalize this. And to generalize this, we made two broad generalizations. One for the types of input data in stateful processing, and one for the types of operators on this data. So for the input data, there's time-varying streams, which are continuously updated, and then there are also static relations, which are mostly historical data, and they're static. So programmable data planes, or these programmable switches, are well suited for the time-varying streams, because they're much like streams of packets. Static relations, which are generally historical data, can be preloaded into the switch from the control plane. And it's okay to do this from the controller because since they're static, they're not latency or throughput sensitive. And now for the operators. Streaming languages are based on SQL, which in turn is based on relational algebra. And these are the standard operators, at least the first three. And I'll show you how they can be implemented in P4. Set operators and joins can require some form of iteration because they can compare sets to each other. And this can be done on the switch using loop unrolling, but only for sets of bounded size. Filtering is also a natural fit for switches. Think about ACLs or IPv4 forwarding. They either filter out packets or update packet header values to route the packets to their destination. Aggregation can also be done on the switch using fixed windows. And stream processing systems extend the standard relational operators to also have windowed operators. We were able to implement count-based tumbling windows. To implement dynamically sized or time-based windows may be more challenging on this hardware. So when we started, we weren't sure whether we'd be able to implement linear road on a switch. And I don't know, it was a pretty crazy idea. We got this benchmark that's intended for software systems, and we got it running on an ASIC at line rate. And in the process, we found the operators that are necessary for expressing these streaming languages. And we found that we can map them onto these hardware abstractions. And I showed you how we manually implemented these abstractions. Don't get me wrong, P4 is great for programming for networking applications. But what we think is next is a more natural way, maybe a language, a streaming language for the switch. So in conclusion, we found that the RMT architecture is a good fit for stream processing. And stream processing generally has changing input streams, static queries running on the switch, and real-time latency requirements, all of which are great for stream processing. Oh. Okay. And yeah, all our code is on GitHub, so you can download it and try life in the fast lane for yourself.
All right, let's thank our speaker.